Yeah, I'd like to tell you about. I had the business of teaching courses in mathematics and design. I actually did this for a number of years over at New Jersey Institute of Technology, NJIT, just up the road. Actually gave me an opportunity, since I was so close, maybe perhaps bring some things with me to show you. And also tell you about this work in progress. For the last 10 years, I've not been teaching this course. However, there's the School of Architecture at NJIT has just instituted a new College of Design. And they're going to begin teaching it. This college is going to start up in September. And they have recruited me to try to bring back this course, which I used to teach, and which resulted in, after teaching it for about 18 years, I actually put together some of the material from the course in my book, Connections, that some of you may know about this book. And you'll find in that, you'll find this book most of the, well, there are 734 diagrams, and most of this book was created by my students. So now, all the things I have over here were primarily created by my students or people I've met along the way. In the process, I actually created another book called Beyond Measure. And you can take a look at this. A number of interesting assorted topics. My travels through this particular area. Matter of fact, some of the things which I have over here resonate very well with the things we talked about during the conference. So let me perhaps start off by giving you a little bit of an overview of this course I have in mind. As I mentioned, this is a work in progress. And now if I can get a main idea from today's meeting. The way I visualize this course is they're carrying on 4 different levels. Highest level being metaphor and creativity, rather than any particular subject. Second of all, 2 and 3 dimensional design concepts, let's enter into it. And then geometry and algebra are the mathematical ideas. And communications and literacy have to be part of this course. And as a matter of fact, I've always been having students writing essays on various things that come up in the course. I have some of the essays over here, so any of you would like to see them. These are the objectives. Topics should be arranged into independent modules. A spiral modeling of learning is used rather than linear models. Concepts return at different contexts. Most topics are connected at different levels. One of the things we see today that you start someplace and you automatically see how it connects with everything else. Each module should contain significant mathematical content because this is going to be a math course. The course addresses a variety of design ideas, symmetry, breaking, duality, positive and negative space, mathematical constraints on space, nature and infinity, modular design, and here are the objectives. We'll be using algorithms to carry out design activities to emphasize rather than the theory. The designs are derived from different cultures, ancient and modern. Most design activities are either adapted to the computer or computer applicable. However, the first stage of the design process should be hands-on on construction. Materials are ungraded. They can be adapted to students from in third grade up to graduate school. Both mathematically and non-mathematically oriented. The course would emphasize writing and communication. Evaluation of students, of course. As a course, you have to evaluate them. Scrapbooks, journals, design projects, homework exercises, essays, no example. Here are some of the main topics. This is way too much for one course. I'm afraid this will have to be a series of courses. But anyway, these are the ideas that I think should be checked into. From informal geometry, start off with, projective geometry, theory of graphs, theory of proportion. Fractals, modular design, three-dimensional geometry in Polyhedra, theory of knots and surfaces, symmetry and music. And see how this resonates with our conference in the last 2 days. Some examples in this presentation, of which I will not be able to get to all of them, are 2 and 3D lattice designs, proportional systems in Roman architecture, based on the silver mean, golden mean, and Le Corbusier's Modular. Star by a Danish engineer named Tony Bruno. Interesting star. Tangrams and Amish quilts, Soma and Lunda tiling, Penguin tiling, hyperbolic geometry, projective geometry and design, Lindenmeyer L systems and fractals, Salvin problem, which I really wanted to get into this course. I'm really so fascinated by it. However, the question is how we can implement this. The application of fractals, image processing, spacing, field, image compressing, music, diatonic scale, and cutting scale. So to start off with informal geometry, I used to start off with just talking about tangrams and Amish quilt. There's a relationship between them. Matter of fact, I have a couple of these patterns here, which let's see. There's the drawing set, and quite versatile. And I simply ask the students to cut these little polygons out, and then try to reconstruct the square if they could. And then after they play around with this, they use some interesting figures, create their own design problems based on these same elements. And so here are a few results. This is a very nice one. This is what I brought in Pennsylvania Dutch country, just to start off with. I have another very nice one hanging in my living room. There's a student's work, and one of my colleagues placed this on the cover of his book. And here's one last one. It's interesting. There are many of these things, and actually these things I'm showing you come from quite some time ago, and they represent a very, very small fraction of what they once was. It's time to rebuild my cache of projects. And there are also, this leads into some interesting geometry based on what we call a zone ground. Here's a 3-zone ground, which actually materializes into a cube. This is an 8-zone ground. You can see, again, almost like the squares and these, but these are not Amish diamonds. I'm going to put this diamond square. And a different diagram. You have ratio of diagonals 1 to the square root of 3. Now this materializes into a rhombic projecting heat rod. Okay, that's the quote hanging on my wall. You notice that there is a 9-square grid. Every quilter begins with 9-square grid. 9-square grid. The 9-square grid is really very simple, but it can be made also very complex. So, well, here is my informal geometry, the coffee can geometry, basically. Just take the top of the coffee can, where you can put a little dot in the center. And then you place the dot on the edge, and then create new dots. And then where the new dots, between any two dots, you can place a line. So you can slowly build up geometry from from up the left-hand corner is called the vesica piscis. And it was in the center of that is where all of the images of Christ used to appear on churches. You can take this quite far into creating some ideas of geometry. Here are some patterns that the students have created from these coffee can geometry. Spirals can come out of very simple squares inside of squares. These are all very simple things to just get started thinking about geometry. Here is that star again, this is a Brunei star, Tony's Brunei star. The most remarkable. But Brunei says that he found this in a tapestry in Pompeii, in the ruins of Pompeii. But I've seen it other places. And in fact, it's sitting right in the little house of Gaudi, the architect Gaudi. I went into his little house on a tour, and there, sitting in the chamber, was in a little glass case, which is a star. And I also went to the Sagrada Familia, over there, in the gift shop. There, you see on the ceiling, this side there. There's an elevator going right to the center. It's quite remarkable. It's very simple, as you can see. You take a square and cut the square in half, place two diagonals in it. Then cut the square in half the other direction. Place two diagonals in each half. And that's it. And I wish I had pointed. I guess I can point. This is a red button in the middle. Okay. You'll see here is a triangle. This is a 2, 4, 5 triangle. In fact, every triangle you see in this whole picture, these are 3, 4, 5 triangles, or fragments of one. So all of these are 3, 4, 5 triangles. The middle ones, the big, 4 different scales. And you can see how it's equally proportioned space, different levels into equally discrete line segments. And here's another view of it. One of my students created this very nice little picture. And then you can see the 9-square grid sitting right there. And there's, I wrote a whole chapter in the later book on this star. It's connected with music and color and all kinds of. Here's another student's like created some nice images of this. There's one. And here's another one. So you can, things come alive and you add color to it. Color is one of the great secrets. You can never find someone who knows about color. That's going to be secret. Here's also the star again. Actually, that star is being used over here to create an interesting tile, which I will talk about in a moment. This is an amazing tile. Theory of proportion. Okay, it's of course the theory as the modular of the and this, by the way, is not, that's meant to be square. The golden mean square, the golden mean cube, and then to the fourth. The way this works, actually, is that these two systems work beautifully. And all proportional systems on the spectrum work the same way. If you get this point out, this length out, it fits right in between these two lengths. In other words, it's the arithmetic mean of these two. If you lower this one to this gap over here, this would fill in and would be exactly at the harmonic mean of these two. All proportional systems have the same quality, so there's the algorithm out here. However, you can it has also additive properties. To add, as you know, to add 1 plus p that p squared adds p plus p squared that p cubed, so it has additive properties, which makes it very architectural. So you can play games here where you take a square and you break it down into rectangles whose edge lengths edges are numbers from those two series, either of those two series. And whenever you get one, you can take the same tiles and rearrange them to get countless others. You can only do this with a system that has additive properties. Try to do that with any other system that does not have additive properties. You get one, that's it. So here we have one tile 3 different ways, here's a second one tile 3 different ways. Okay. And here's what the Fabrizio does with this. He creates, this is too bad. It looks like my, you irritated the habitation and parts using similar aspects of the physics. This is a system based on Roman proportions, and which is based, instead of about golden mean, this is based on the silver mean. And basically there are three rectangles of 3 different proportions: a square, a square root rectangle, and one which I call a Roman rectangle, which is 1 by 1 plus the square root of 2. 1 plus the square root of 2 is known as the silver mean. And you can see here that there are all kinds of relationships between these three modulars. You take the Roman rectangle and extract the square, you get the square root over here. You extract one square from two squares from the Roman rectangle, you get another Roman rectangle over here. So they fit together in all kinds of ways. If you take a fourth square root rectangle and fold it in half, you get 2. So there are all kinds of ways to go. So this leads you to be able to create some very interesting patterns, because what if you, so I gave it to students to create a pattern by taking these 3 species of rectangle and creating a pattern that where the rectangles occur at 3 different scales. So let's see, here's one of them. these rectangles occur in 3 different styles. You may have some other ones here. Yeah. This is another one. And it's always fascinating to me that if you give very general instructions without being too specific, you get back results that are quite different from each other. I should have mentioned that you can do something similar with the golden mean. You just take triangles, which is a triangle, which is a golden mean. The ratio of the base to the side is golden mean. And you can dissect that into 2 golden mean triangles and create other patterns, which here's one of the students' patterns based on all golden mean triangles. And here's another one. They're all triangles which well, actually these are triangles are put together to make rectangles, make diamonds. And here's another one, just to put the idea of the diversity of them. And you'll notice that golden mean has intrinsically based on the number 5. So it comes out without thinking about it. 5 always comes out. 5 or maybe 10 with that. So okay, here's here's the algebra behind the system I just showed you. There's an algebra here, and whereas in the modular system there were just either the red series or the blue series. And in this case, there are an infinite number of geometric sequences. These are all geometric sequences. But what I just would like to point out is that if I raise this number here, this turns out to be the arithmetic mean of these two. If I bring this one down, it turns out to be the harmonic mean of these two. So this system, again, has that wonderful mark of what I consider a really good proportional system. So it starts off with geometry and simple geometry, but then it can get rather sophisticated. And and I have work done by a couple of architects who have actually investigated the ruins in the city of Ostia, which was the port city of the Roman Empire. And he has discovered this Roman system essentially being used consistently. Oops. Here are some tiling patterns, a number of tiles. That tile I showed you before is a cookie tile. I think it's very interesting. And here are some, I should just show you one very nice. We heard with the other saying different technical criteria to facilitate this process. So what we'd like to do is to minimize this and then open up some of this Okay, that's it, yeah. This is my friend, my good friend Slavik, has done a lot of work with these tiles. You can see in green, there it is. Those green tiles are just nothing more but a tile with a bunch of stripes down it, vertical stripes. And the green tiles are being turned at right angles. And he discovered that he and also independently another friend who I introduced him to, Dan Nicholson, out in Chicago, interesting architect and artist, both mutually discovered that all the labyrinth patterns are basically can be created in this fashion. Very striking. Getting back to this, you can see a number of these tiles, up tiles at the bottom, we call them up tiles. You can see I've taken this off there, green tile. And it's much more interesting to see dynamically. And here is simple enough, but look at all the wonderful patterns you create. This two-shift tiles. Two-shift tiles. And what I'd like to be doing with the students, I have some little metal trays, and I made a bunch of these, and I would put them on little magnetic tape, cut them out, and then just be able to push them around on this little metal tray, and then use that as a way of studying symmetry patterns. See how many different symmetry patterns you can create in a particular arrangement. So that would be a project that I'll try to do in the next course. Yes, now there is that tile I showed you, from the Buddha star. It's a kuki tile. It comes in two. This is the negative or the positive. Black becomes white, white becomes black. And this layer is all done with sequences of the kuki tiles. The Slavik script. Here are some of the, Ben Nicholson has been coming up with complete taxonomy of labyrinth patterns. And you can see that once again he's using these up tiles to create labyrinths. So this is something that would be very much fun to work with students, just playing around with this. You can see you can begin to turn them into circles and create labyrinth patterns. Here are some of the cameo stone knives. It's called stone knives. You put the natives simply place little stones on the ground, and then create continuous curves surrounding them, and to create interesting patterns. And they became very excellent at doing this. There's an ethnomathematician by the name of British, DES, and he has actually made a great study of these patterns, and he found incredible amount of mathematics in them. I have one of his books if anyone wants to take a look at it. It's very fascinating. And discovered that these patterns are created by taking mirrors, putting the mirrors in there, and then taking just a ray of light and hits the mirror, it bounces off. And then here you can see the diagram, the patterns being made with the use of mirrors. So these are mirror curves. And actually, Erica Mayen has actually fell in love with these and began to investigate them from the point of view of graph theory. So we wanted to see how many different maps you can create from one, which have diagrams with one intersection, two intersections, or two pieces, or three pieces. And these kind of games with them from the point of view of graph theory. So you can go from the actual mathematics into the mathematics. 3 minutes? Okay, that's fine. Here are some Roomba patterns based on right from the same patterns. Let me move to the. I have a whole bunch of lattice patterns which are created from lattice. And all you do is count. You can create your fundamental pattern, just count the numbers, and then the style. Or you can do this with fourfold symmetry. And I have many examples of this. Or you can do it in 3 dimensions. There's a lattice design which is done in 3 dimensions. And there's a marker. Automatically fits together. All you have to do is count squares, or count cubes. Counting cells and counting. Symmetry in music. Well, this might be interesting just to show you between the end here, actually. There's your 12-tone circle right up there that you see earlier today. And there's the piano. Of course, D is on top. And D is on top because that is the more symmetric. That's the diatonic scale. The D on top is totally symmetric. And you can see why. Here's the piano. Here's D on the piano. And you notice the D, on the middle D, divides this pattern into symmetrical. It's very symmetrical around D. Here is there is a diatonic scale, 7-tone scale, based on D. And if you turn it upside down, the white notes become, the little white dots become black dots, and gives you a pentatonic scale. The pentatonic scale is distinguished from the heptatonic scale because there are no half tones, no semitones. So almost anything you play on a pentatonic scale, play the black keys on the piano, it will sound like music. You have to be a really good composer and musician to be able to work with those half tones. But what somebody in Tucson at the University of Montreal discovered is that most mysteriously, all the African clapping patterns are based on the diatonic scale. The diatonic scale occurs in all different modes. You can rotate this so C is on top, you lose its symmetry. And you still have the diatonic scale, because you have a different clapping pattern. So this clapping pattern will go and if you put C on top, you get a different clapping pattern. And here are some music with clapping based on Reich's, Stephen Reich's music. And let me.
Okay.
Last weekend. This is.
Well, I like your idea of constraints.